So for regression equations, we're going to look at some different things, some different data sets. And when we're working with these values, sometimes this data tends to fit into a pattern. And this pattern can be called correlation. Now, there are multiple types of correlation that we can discuss. They can increase over time, and if my correlation is increasing, then it is said to be positive. Or my correlation can decrease over time, and that's said to be negative. So let's think about these two different types of correlation and then examples that go along with them. The longer that I study, the higher my test grade should be. Now, the reason this is correlation is because there is a pattern, but if you accidentally study something that's not going to be on the test, let's say you're studying Spanish and it's a math test, then there is not a direct cause that the longer you study, the higher your grade will be. But again, it does fit the pattern that if I study the correct stuff, so if I study my test 10 materials, the longer that I study, the higher my test grades can be. Now, for a pattern to be negative or to decrease, we think about things like weight loss. The longer that I am on a diet, the lower my weight should be. So as the days progress, the longer that I'm on this, as my X values increase, as I'm on the diet, then my weight over time should decrease. So if I look at these three examples, I can determine what type of correlation is by simply drawing a line through the middle. So for this first one, I see that it's increasing. This will be our positive correlation. For our second one here, if I draw my line through the middle, I can see that these values are decreasing, so this will be the negative correlation. Now for this last one, if I were to draw a line, there's not really a good line that I could put on this in order to determine the pattern that my points are following. This is what we would call no correlation. And the way that I think about this, if I were to take a cup full of beans and shake it up and then throw it into the air and watch where the beans would fall on the ground, then this is kind of what it would look like, a nice scattered pattern. So there's no direct correlation. And so to name this, we would say no correlation. So one way to analyze the correlation is to use what we call a correlation coefficient. The correlation coefficient is a way to model the set of data and the trend that this linear function has. Now notice we're only going to talk about linear trends here. There are quadratic regressions and exponential regressions, but in this class, the main thing that we're focusing on are linear trends. So, as we go through to look at these, the R value is going to represent our correlation coefficient. Now, the correlation coefficient is going to tell us how close together our points are. So is the pattern a strong pattern, or is the pattern just one that I can barely see what's happening? For positive correlations, the positive correlations, the correlation coefficient will be positive. You know, that sounds weird. And R is going to be closer to 1. For negative correlations, the correlation coefficient will be negative and is going to be closer to -1. Now, 1 and -1 are going to be my extremes. So all correlation coefficients fit between two values. So my R value, remember we said was the correlation coefficient, falls between -1 and 1. So if somehow you put this into your calculator and you figure out that R is equal to 3, you know that's going to be incorrect. R can be -1 all the way to 1. Even if it's 0.99999, that tells me that it's a pretty strong pattern, and they're going to fit a linear trend. Again, these are linear trend lines that we're looking at. So it would probably help if you draw yourself a little number line. And on each end, we want -1 and +1. We also can talk about our correlation coefficients as being strong or weak. So as I get to the extremes, this is where I would call a strong positive correlation. Why? Because I'm closer to 1. Same thing at -1, this is going to be a strong negative correlation. So if we think about kamikaze pilots, they are extremists, but they believe so strongly in their cause that they are willing to kill themselves in the act. So if I am on either extreme, that means I have a strong correlation. It just depends on whether you're on the positive or the negative side. Now, as you get closer to values like -0.5 and +0.5, this is where we start to call our correlation more weak. So if it's on the negative side, it'll be a weak negative. If it's on the positive side, it'll be a weak positive. And that would be that our lines or our points are close together. We can still tell the direction, but maybe not the most perfect pattern between them. And then as we get right here at 0, that's when we say that there is no correlation. My points are just scattered all about on the graph. So let's look at these examples, having the number line that we have there. And again, the closer together that my points are, that is going to be the stronger that it is. So I can tell that this is increasing. So I would call this a strong positive. We go here. Now I can still tell that there's some kind of positive trend going here, but notice how all my points are much more spread out. So this would be a weak positive. For the third one, I can tell that we're going downhill, and all those points are very close together. In fact, they almost all touch my line. Therefore, that'll be a strong negative correlation. Finally, you see the last points are more spread out. This is what we would call a weak negative correlation. So the closer together my points are, my dots are, my data is, that means the stronger it is. And then we just see the direction of it what it's going, whether it's increasing or decreasing, to determine whether or not it's positive or negative. So in your calculator, this is using the black calculator. You want to press the data button. You're going to have two sets of data here. These could be between your shoe size and your height. It could be your weight and your height. It could be your weight and your shoe size. There's any two types of numerical data that we're going to compare. So first thing we'll do is press the data button. In L1, we'll put our X values. In L2, we'll put our Y values. Then we want to hit second data. And when we hit second data, we want to scroll down to the fourth option. And that fourth option is going to be the linear regression. Once you find it, hit enter. Make sure that you have L1 and L2 selected for your list. Your X list should be L1, L2 should be your Y list. You want to make sure you can scroll down to calc, which stands for calculate, and then hit the enter button. When we see this, we will have the A and B values. Our A will be the slope of our line, and the B will be the y-intercept. Now we can round these to the 10th place or 1 decimal place. And then we also want to record the R value, which we just talked about as being the correlation coefficient. So what the R value is going to end up telling us is how good is the line that I just came up with a fit for my data. And if it's a great fit, it'll equal 1. That means it's perfect. All my points fall on the line. The closer it is to 0, the worse the line is for me. Now there are two other options when we come up here for the linear regression. There is a quadratic regression. So if they ask for a quadratic regression equation, you would choose that option. And there's also an exponential regression. And you will be able to tell whether or not I need to use a regression equation, a quadratic regression or an exponential regression based on the shape of our data. We know this by analyzing the different types of graph. Quadratics will have the U shape, where exponential is going to have that J curve. So if you can see the points on a scatter plot and they look like a straight line, we know we want to use a linear regression. If they look more like a U, we want to use a quadratic regression. And if they're that J shape, they have an asymptote, that flattened area, that's where we know we want to use exponentials. But again, we are mainly focusing in here on linear regressions. So as we look at the first example, so the night before the last math test, Shaniqua and her study group had a study group at her house. It was a great night. They ate a lot of pizza, did math, and they laughed a lot. Shaniqua scored better on her test than usual and thought it might be related to the pizza. So she collected the following data from her friends in the study group. We can see how many slices of pizza each person ate, and then their increase of points on their test score. So the first thing we're going to do is we're going to take out our calculator, and we are going to want to type in this data. So in L1, you'll do 2 enter, 6 enter, 1 enter, 4 enter, 3 enter, 5 enter. And then in L2, you'll want to type in 5 enter, 9 enter, 4 enter, 7 enter, 6 enter, and 8 enter. Once you get your values put in L1 and L2, remember you're going to hit second data. Once you hit second data, you're going to look for option number 4, the linear regression. Make sure that your X list is L1, that your Y list is L2, and then calculate and enter. And again, remember that we are looking for an A value. We're looking for a B value, and that's going to help me create the regression. Remember, my regression line is AX plus B. So for my A value, I get 1. For my B value, I get 3. Then we're also going to look for the correlation coefficient, which is the R value. In this case, our R value is 1. So we're going to take all the data that we've collected from the calculator and put it together. So for the linear regression, Y will equal 1x, so I'm just going to put x plus 3. Here's my regression model. So if I wanted to predict how many increased points I would have on my test, because remember the number of slices of pizza was x and the test score increase was y, I would put how many pieces of pizza into the equation. If I ate 3 slices, I would plug 3 in for x. 3 plus 3 would mean that I would increase my test score by 6. Now for the correlation coefficient, that's my R value. And we got the R value to equal 1. So based on this correlation coefficient being a strong positive, would you recommend eating pizza the night before a big test? And I would say yes, because you are almost determined that you will increase your test score if you eat pizza. So then we're going to look at example 2. Now, you can notice some things that are happening from your data here in number 2. We have much larger values, and that is okay. So we're going to use our calculator to go in first and determine all the values that I need. So my elevation will be my X value. Temperature will be my Y. So in L1, hit data. L1, I'll need to put in 1,000, 5,000, 10,000, 15,000, 20,000, and 30,000. In L2, I will need to put in 56, 41, 23, 5, negative 15, and negative 47. Remember, once you have all your values in, that's when you want to hit second data. You'll go down to option number 4, the linear regression. And when you hit enter there, you are looking for the A, the B, and the R values. Remember, A represents our slope, B represents the y-intercept, and R is the correlation coefficient. So as we're working through this, I get A to be negative 0.00357 and B to equal positive 58.797. While I'm here, the R value in this case will be negative 0.998. Now, if we remember from the notes in the first part, it said that we can round to the tenths place, or just one place behind the decimal. Now, I don't want to do that here because that would just round to 0, so I'm going to say that the 5 is going to tell my 3 to round up. So that'll make my slope negative 0.004. And here I can have the 9 tell the 7 to round up again. So that'll give me plus 58.8. And so that's going to be my regression equation for this. Now, the one thing I did forget here is you have to make sure you have the x. That's how we know that that's the slope, because it is attached to my x. The correlation coefficient is just the R value, which is negative 0.998, which would tell me that this has a negative correlation, and it's pretty strong. So the next question is pretty simple. Is it positively, negatively, or not correlated? Negative, because the R value here is negative. And I would even go as far to say this is a strong negative. Now for the last part of this equation, it says use the equation to estimate the temperature at an elevation of 12,000 feet. So all I need to do is take this equation that they gave me, that we found, and plug in 12,000 for x. So y equals negative 0.004 times 12,000 plus 58.8. And you just need to put that directly into your calculator. And when you put that into your calculator, you should get 15.6. So the temperature at 12,000 feet, I will predict to be 15.6 degrees. Now my next question, we look here, gives me the opposite. Use my equation to determine the elevation if the temperature is 70 degrees. So now I'm given the y value of 70, and I have to work backwards to find what my elevation will be. So, like most equations that we've solved so far this year, I'm going to start by subtracting 58.8 from each side. When I do that, give you time to put that in the calculator. You should get 11.2. So I'm just going to bring down the other side. Negative 0.004. And again, remember that we are trying to find the x value here. So my next step will be to divide each side by negative 0.004. Okay, so I'll give you just a second to plug that in. Alright, and so when you type in 11.2 divided by negative 0.004, you should get that my x value will equal negative 2,800 feet. So what this means is that we would be, in this equation, predicted to be 2,800 feet below sea level to have a temperature of 70 degrees. As we look on to the next example, it says the amount of antibiotic that remains in your body over a period of time varies from one drug to the next. The table shows the amount of antibiotic X that remains in your body over a period of 2 days. So here, my time will be my X values, and the amount of antibiotic that's left in my system will be my Y's. So this says generate. Notice it says here the linear regression equation. And so if it tells me to calculate the linear, that means I'm going to, in L1, put in the time. So 0, 6, 12, 18, 24, 30, 36, 42, 48. And then in L2, I'm going to put in the amount of antibiotic. So 60, 36, 22, 13, 7.8, 4.7, 2.8, 1.7, and 1. Then I'm going to hit second data, linear regression, so option number 4. And then find my A, B, and R values. Make sure that your X list is L1 and that your Y list is L2. So for my A value, I get negative 1.07. For my B value, I get 42.26. And for my R value, negative 0.88. So if I'm going to turn this into an actual linear regression equation, I just put it in y equals mx plus b, or in this case ax plus b, because a is a predicted value. So negative 1.07x plus 42.26. And then I can tell here by my R value that this is a negative correlation, and I would still consider that to be pretty strong. Now part B asks us to notice how it's changed here, calculate the exponential regression model. So I already have all my values into the calculator. At this point, I just need to hit second data. And instead of choosing option 4, I'm going to find the option that says exponential regression. Again, your X value, your X list needs to be L1, your Y list needs to be L2, and then you hit calculate. When you click calculate, you should get your A value to be 60.4. Your B value should be 0.92. And then my R value would be negative. And we find our R value here is negative 0.999. So as we look at our questions, looking at the correlation coefficients, which model is better, meaning which model is stronger, where are my points more closely together? And that is going to be in the exponential model, because you notice negative 0.999 is closer to negative 1 than negative 0.800. So in this one, the exponential model is better. And we can tell that again by looking at our R values, the correlation coefficient. So using that specific model, the next question. So using our exponential model, estimate how much of the antibiotic will be left in our body after 10 hours. Now, one thing we have to make sure that we do here is take the values that we got and put it into an exponential equation, which we know is y equals a times b to the x power. We learned that from our knowledge of exponential equations. So they want us to plug in 10 hours for x. So I take my values. Y would equal 60.4 times 0.92, and I raise that to a power of 10. And all you have to do here is plug that straight into your calculator. And when you plug that into your calculator, you should get 26.2 milligrams of the antibiotic is left in our system. And that is how you find regression equations.